I hope you can see everything.
Yes.
Great, that was quick.
Great. For our last talk of today, we have Rainer Klages, who will talk about extended Poisson-Kac theory, a unifying framework for stochastic processes with finite propagation velocity.
C'est comme ce qu'on voit comme film, ils mettent sur le projecteur comme ça.
Wait, I need to mute people.
Okay. Yeah, there are some voices in the background. Okay, I guess I can start.
Yes, indeed, the mute police is working.
Okay, great. Yeah, so first of all, I thank the organizers very much for inviting me, and I do apologize that I cannot be there in person. In fact, my planned stay in January was canceled due to Corona, and now I have heavy teaching duties. So it's really a pity, but I'm happy that at least I can give a talk now. And secondly, well, the framework for my talk was very nicely put by Edi Barkay's talk this morning, and in particular, Sergei Fedotov's talk, who very nicely set the frame. And indeed, what I'm going to talk about is very much inspired by Sergei's work, who really pioneered that, as you will see. So we draw very much inspiration from Sergei, and thank him for this. This is joint work with my colleague Massimiliano Giona and Andrea Caroli. And I have to say that Max is really the mastermind behind this project, an expert on Poisson-Kac processes. And my contribution was rather to make him aware of the existence of Levy walks, and then to ask the question of how to combine these two fields. Okay, so indeed, as has been discussed extensively this morning, I don't have to make a big point out of that, namely the problem of unbounded fluctuations. Here as an example, you see two generic processes we are all well aware of. On the left-hand side, you have Brownian motion in 2 dimensions, an example of a trajectory. On the right-hand side, Levy flights, where actually the flights would just be the Levy dust, meaning the turning points of the trajectories. Actually, this would rather be a Levy walk to make more clear what's going on. And both can be generated from what a physicist would call an overdamped Langevin equation, which is this one here, where for the left-hand side, certainly you simply put in Gaussian white noise with the respective strength squared out of K. And if you want to have Levy flights, you would just put in alpha stable Levy distribution. So that's how you could generate these types of dynamics. But now the problem is, as has already been discussed extensively this morning, that in both cases, by definition, the fluctuations are unbounded, meaning there can be, in a physical sense, jumps with infinite velocities. Because of the unbounded tails of the distribution, they both live not on a compact support. So now you may or may not worry about that. Of course, you may argue, well, physicists have been dealing with so-called Langevin dynamics for a century at least, and it has been widely applied for modeling physical phenomena. And unbounded fluctuations, of course, can only occur with a rather small probability, so why should we care? However, especially if you consider Levy processes, as has been discussed, then the implications of unboundedness are even more serious in the sense of non-existence of moments of second and higher order. So then if the moments are not defined, for example, if you're thinking of energies, we just heard about that, and if you would ask an experimentalist, say, to measure the second moment of a respective distribution, it would not exist, and one would be in trouble. So it depends in a way on anyone whether or not one would be interested in bounding the fluctuations, but there are also from a physics side good reasons why one should be interested to study the consequences. And indeed, they have also been seen in some experiments, say on diffusion in rare gases, on photonic transport, and in superfluidic helium. So there are some consequences of bounded fluctuations, and I'm going to discuss this further. Okay, so now the problem is, how do we get from these standard processes with unbounded fluctuations to processes with bounded fluctuations, or with, as physicists would call it, with finite velocities? And here, first I constrain myself to 1 dimension to keep things simple. If you think of Brownian motion, there is the famous Poisson-Kac process that has been invented, I think, in the middle of the last century, actually first by Taylor and Goldstein, but perhaps the most prominent formulation then became known by Mark Katz in famous lecture series in 1956. So a Poisson-Kac process is defined by this equation, meaning you now assume that you have a constant velocity, thus avoiding the problem of infinite velocities per se. And you simply sample the times by which a particle moves in one direction from a Poisson distribution. So it is a Poisson process chi of t and lambda, so with rate lambda. So that means in one dimension, the particle moves with a certain velocity in one direction. And after a time t sampled from the Poisson process, it switches the direction. Very simple. And it is a well-known result that if you use the diffusive scaling, meaning the so-called Katz limit, then you can recover the well-known Wiener process. So it's contained in this Poisson-Kac process as a special case. Now, if you think of Levy processes, one can here bound the fluctuations by defining Levy walks, as has been extensively discussed this morning already. And here I consider the special case of a so-called two-state Levy walk. For example, Sergei mentioned the velocity Levy walk, which is a little bit different. The two-state Levy walk is defined like that. So here you have the position for the equation for position at the nth transition in space. And you see here that after flight time tau n, you simply flip the direction of the velocity. And S naught is just the initial condition with which you start, where you may sample the direction with equal probability. And in particular, for Levy walk, the tau n, so the flight times, are drawn from a power law tail separator type transition time probability distribution function. So this model was first set up in work by Schlesinger, Klafter, and others in the 80s. And this here defines the equation for the physical time. And yeah, this is here the equation for the power law distribution that is often used in order to find the transition time PDF. So this is the analog of the Levy flight process that you have seen before, but all these processes now just exhibit bounded fluctuations, so finite velocities. Now you may ask the question, how are these two processes related to each other? And the answer, if you start from Levy walks and then look at Poisson-Kac processes, is very simple. It's just a trivial fact that, of course, that you can obtain the Poisson-Kac process from Levy walks if you simply replace this power law distribution by an exponential one, and then you're done. And indeed, this has been discussed already in a paper by Campos and others in 2015. They called this actually Brown and Kuiper, not being aware of Poisson-Kac processes, but they already worked that out to some extent. So this direction is very easy, meaning Poisson-Kac processes are a special case of Levy walks if you just replace the power law PDF by an exponential one. And indeed, you can make this more explicit, and this is a very nice trick that, for example, is contained in the paper by Sergei and others. So you may simply rewrite the power law PDF in this form. And this very strongly relates to Sergei's talk, actually, because here you see explicitly that we have time-dependent transition rates. So you obtain the power law, actually, if you choose this particular form for the time-dependent transition rates, and then if you work it out, you get simply the power law you have seen before. But this really gives a very nice physical interpretation, because if you set the transition rate to simply a constant, then you recover the exponential distribution at the Poisson-Kac process. But if you make the transition rates time-dependent, then you increase the persistence in terms of physics. And that's exactly what Sergei was talking about. And this is also actually what you can measure to some extent in experiments, and what Sergei and colleagues have measured in experiments. So this is very relevant. Now, this is a very simple trick, but it has many consequences. One of them, that the introduction of time-dependent transition rates enables one to write down Markovian master equations for what one may call partial or structural probability density wave functions. Again, this is what we learned from Sergei, what he explored in quite some of his papers. So you can very nicely write down these master equations for the two probability density waves, one going to the left and one going to the right. And they have a very simple structure. And the big advantage is that they are Markovian, so they can be handled mathematically very well. Of course, they need to be equipped with suitable initial and boundary conditions. And indeed, you can then straightforwardly show that you can obtain the well-known Cattaneo equation that defines Poisson-Kac processes as a special case, and the Levy-Walk case has actually been worked out by Sergey in PRE from 2016. So, summary so far, this was more or less literature review, but what I have shown to you so far is actually summarized in this picture, meaning actually these three circles. So that means if you start from conventional Levy walks, then Poisson-Kac processes are contained as a special case, and indeed a very similar case of Poisson-Kac processes is Levy processes. So we have clarified this direction, and here you see just examples of trajectories for these different processes. Now you may ask yourself, okay, but now can we actually go further? Meaning, can we invent a new version of Poisson-Kac processes from which we can derive Levy walks? And this is the question I'm now going to discuss. And indeed, the answer is yes, you can do so by designing what we call extended Poisson-Kac processes. And this yields actually a new theory of finite velocity stochastic processes, which is based on these generalized transition rates we have seen before, which very nicely capture non-trivial spatio-temporal correlations. And now I'm going to explain to you of how to do this. Now, the first step to go towards extended Poisson-Kac theory is to use exactly this idea of time-dependent transition rates, meaning that the transition rate lambda is not a constant, but depends on the transition time to generalize these Poisson-Kac equations you have seen before. So this is actually the Poisson-Kac equation you have seen before, where you have a Poisson-Kac process if you simply assume a constant transition rate. But now, as we have seen before, for Levy processes, this transition rate may depend on time. So why not simply plugging this into the original Poisson-Kac equation as we do here? But then you need a second equation, meaning equation actually defining the transition time and the relation to the physical time, which is stated here. And this is, in that way, a generalized Poisson-Kac process, where, as I've said, the transition rates depend on time, where tau is actually the time after the last velocity transition. So meaning where then the particle switches velocity for Levy walk. Of course, you have to supplement this dynamics with respective boundary conditions, and in order to preserve the continuity of the position in space under at the switching, then you identify the position if you approach the switching time from above and below. And also, you may simply set the switching time equal to 0 after a transition has been completed. So this enables you to indeed recover the Levy walk from a generalized Poisson-Kac process as a special case. And indeed, you see by definition, here we now have a non-autonomous Poisson-Kac process, as we have time-dependent transition rates. So this is a straightforward generalization, but now you can play around a little bit further with this formalism. And as is well known, say, from dynamical systems theory, if you have time-dependent dynamical systems that depend on an external force, like a periodic kick or something, you can certainly embed these processes in higher dimensions, and we do the same here. So we simplify the previous formalism by now introducing new state variable y vector and generalized velocity vectors p vector as follows. So we simply define the y vector as by the components of the position and the transition time. And accordingly, we define two generalized velocity vectors by the constant velocity with a respective direction, and this is just a dummy variable because the second component denotes the transition time. But now, if you rewrite the respective Poisson-Kac equation, we can write it in a more compact form like that, so in vector notation. But again, now this has interesting consequences. Namely, now with this set of state variables, we are working in this state space, meaning it consists of the position space and the transition time space. But now in terms of transitional parameters, we have this space. So where S defines the generalized Poisson-Kac process with the time-dependent transition rates and the transition times. And now you see actually here we have what we call an overlap. So meaning the intersection of these two sets is non-zero, because both are coupled to the transition time. And we call this non-empty intersection an overlapping Poisson-Kac process. So there's an overlap here, which is a kind of interesting mathematical property. So the message is that you can obtain Levy walks from a generalized Poisson-Kac process as an overlapping Poisson-Kac process. But now, in fact, you may ask yourself, well, okay, if you want to have a Levy walk, we need an overlapping Poisson-Kac process, but is that necessary in general? And the answer is no. Of course, you can design generalized Poisson-Kac processes by simply eliminating or by breaking the overlap. And this leads to the concept of extended Poisson-Kac processes. That means you may simply ignore the overlap and design other stochastic processes like that, where the state space simply depends on X, and you have the same space of the transitional parameters as before. But here, by definition, you don't have any overlap, and that means we break transitional coupling. We have transitional asynchrony. So this would not define a Levy walk, but some other process. And this yields our most general formalism, and I define this in higher dimensions, but I warn you, if you're more mathematically minded, the following is a sketch only. So I skip any more elaborate mathematical details. There are in our respective paper if you're interested. So I just want to give you the flavor of it. So now we may further generalize this whole concept by assuming that we have stochastic parameters, which we denote by an alpha vector that depends on t. And this is a capital sigma. So this in a way replaces the previous generalized Poisson-Kac process. So you may generalize this by introducing this set of stochastic parameters that may depend on physical time t, some transition rates lambda, and more generalized parameters. And the transition time tau, you may assume that this follows some Markovian transition dynamics with a given rate, say mu, that may depend on x and tau, and some given transition probability kernel, capital M. And in this case, the corresponding extended Poisson-Kac equation would read like this, where in addition to what we have discussed before, we have also introduced a biasing velocity field, so bias, given like that. And this is what you have seen before for the ordinary Poisson-Kac process, just suitably generalized. So you see here we have a generalized version of these generalized velocity vectors defined accordingly. So that really means we generalize the previous Poisson-Kac process in many ways, which gives you a very general, very flexible theory to model all kinds of different stochastic processes. And now I just flashed to you the corresponding master equation that one can derive or write down for this process, but I do not expect you to understand that or appreciate that in full detail. So because it looks fairly elaborate, but this is just to give you an idea of how one can set up this whole theory and what one can do with it. So this is the master equation for what we call extended Poisson-Kac processes for the full probability density P, defined on the respective space of state variables and transition parameters. And you see the structure is rather clear. Here we have the three flux terms here with respect to position for the biasing fields, and here for the generalized velocities. And this is the respective derivative with respect to the transitional properties. And here you have the two transitions defined by respective stochastic processes, here for the transition rates, and here for the more general parameters. So this is something you can play around with mathematically, and which you can define in this general way. Now, let's move a little bit back to physical reality. What I now want to show to you is of how to boil down this very abstract general mathematical formalism to solve some physical problems. And I would like to show this to you by discussing three specific examples. The first one, one may call transitional senescent random walks. So this is motivated by experiments on cell division, meaning it was found in this paper in the 60s that cellular division stops after a certain number of mitotic events. And this motivates mathematically to invent a model which one may call senescence, which in a way is very closely related to what physicists call aging, But if you wish, this is aging in the number of transitions, not directly in the physical time. So this is in a way the basic difference. So here we simply define a random walk with a transition rate lambda and walker velocity v where both become functions of the number of transitions capital N. So these would be the respective spaces we're working on. And again, you see here, we define it that way that again, we have an overlapping Poisson-Kac process. And for this one, one can straightforwardly write down the master equation for the partial probability density waves. And this is how they look like. And you see that these equations depend on the number of transitions. So this is the respective value for the transition number capital N. And these master equations you can actually solve, but in fact, first you can generalize this process to define senescent Levy walks. That means you simply have to include on top of that the transition time tau, and you can write down respectively generalized master equations. Now we define that after any transition, the transition time tau that depends on n is reset to a respectively larger value to model this kind of aging or senescent phenomenon. And indeed, here, if you then do simulations, one can find that senescence actually enhances the superdiffusion you find in Levy walks, which is not too surprising, because if you do exactly this type of modeling, then certainly by definition you increase the persistence, and therefore you would naively expect that you enhance the superdiffusive properties, and that's exactly what we see in respective simulation results. So this is the first example. The second example is a process that has been widely studied over the past few years, which is known as Brownian yet non-Gaussian diffusion. And you can also recover that within this generalized or extended Poisson-Kac setting. There were many experiments, especially on intracellular transport, where it was found that the position mean square displacement grows linearly, while the position PDF shows non-Gaussian exponential tails. And this was reproduced in terms of stochastic modeling, first by so-called superstatistics invented by Christian Beck and Eddie Cohen many years ago. And then this was further generalized by the so-called concept of diffusing diffusivity models. These latter models are defined by a diffusion coefficient that performs some stochastic dynamics. And by using this type of models, these experimental results could be reproduced. So these models yielded non-Gaussian position PDFs with exponential tails, at least on shorter time scales. And in fact, we can also obtain that for finite velocity processes within the framework of extended Poisson-Kac as follows. So we introduce a Walker speed that now changes over time according to a Markov chain dynamics, like that. So we introduce some randomness on a more microscopic level than was done in these models. So for superstatistics, you simply average over predefined distribution of diffusivities, and here you introduce randomness in the diffusivities. Here we introduce them on a more microscopic scale directly for the microscopic velocities. And this is the corresponding Poisson-Kac equation, where you see the difference is that now these betas depend on time. And here we have a non-overlapping Poisson-Kac process because that's how the spaces look like. And again, you can write down a master equation, and here it can also be solved to some extent. And by doing that, we find that we do recover the exponential so-called Laplace distributions for short times that have been derived from other theories and that have been seen in experiments. So again, as I mentioned, our approach gives a slightly different touch on the explanation of these exponential tails, because here they can be understood in terms of Markovian recombination on the level of the microscopic velocities. And now let me conclude by briefly discussing a third model that you can set up within the extended Poisson-Kac formalism, which in fact are subdiffusive Levy walks. So now you may define transition rates described by a Markov chain dynamics. So now we let the transition rates fluctuate randomly on a bounded interval. And in this case, the extended Poisson-Kac equation would look like that. So note again that here the transition rates depend on time, but not on transition times. They are just some stochastic process. It's just a Markov chain. In this case, there's no overlap of any spaces. And now, if we assume a power law form for the equilibrium density of the transition rate process, this actually yields a power law transition time PDF. And in the long time limit, we do recover Levy walk dynamics. As known from standard Levy walks. This we could verify analytically and numerically in simulations. However, now, if you play around with this process and assume that there's no invariant density for this Markov chain dynamics, but instead that you have a shift to progressively larger rates, then indeed we kind of suppress this Levy walk superdiffusion. We do obtain subdiffusion in the long time limit. At least we do have some numerical evidence for that in terms of simulations, and an analytical theory for that is still missing. Okay, so this is what I wanted to tell you. So to make you aware of the outline of extended Poisson-Kac processes and giving you some examples. So just to summarize, I hope I have not now conveyed to you the general picture as outlined here, namely that you can construct a theory that we call extended Poisson-Kac theory, from which we can derive the theory of Levy walks, Poisson-Kac processes, and Wiener processes as special cases. And it enables the modeling of non-trivial spatial temporal correlations if you play around with the microscopic definition of the transition rates, which may be complicated time-dependent processes. And you may also plug in non-trivial temporal dynamics for the microscopic velocities. So it is a very flexible scheme. And as you can then state Markovian master equations for the partial probability density waves, it still enables a mathematically analytical access road to solve problems to some extent analytically. So what I reported in this talk was mainly what is contained in this paper, which is going to be published in PIX. It's just in print. The preprint is available on the archive. And I may say that this paper just sets the scene for this whole theory. And we have already worked out this theory to some extent. For example, we have studied aging based on these concepts of Levy walks. And indeed, we have also then studied spectral properties of this type of stochastic processes in another paper. And there's also a paper submitted on consequences with respect to the central limit theorem. And in another paper, we're also going to study fluctuations, spatial relations related to this type of processes. Okay, thank you very much for your attention. Yeah, that's all what I wanted to say.
Okay, thank you, Rainer. Let's thank Rainer one more time, or one time. And do I have questions in the room? Okay, but it seems Enrico has a question from Zoom. Actually, so Enrico, please unmute yourself and ask the question.
Yes,
hello.
Can you hear me?
Yes, indeed.
Yes. Oh, very well. Hi, Rainer. Nice to meet you, even if virtually. So I wanted to ask you a question related to the master equation, or if you like, you had this extensive set of terms.
Yes.
Yes. So essentially, non-localities emerge from the integral terms.
Yes,
So
exactly.
you have their non-locality in possibly in space and in time.
Yes.
So
yes.
the first, okay, yes.
Exactly.
So that's why you can get, so essentially not always your theory has a Markovian process underlying, but it can have non-local semi-Markov, for instance, etc. Okay.
Okay, and that's actually the master equation for the full probability density P.
Yes.
And the point is really that you can also write that down in terms of these partial probability density waves. And that's really the point, which are then Markovian. So I have here this P plus minus. So this makes a big difference.
Yes.
So I haven't shown that for this. I haven't shown that for this generalized process, but there you can do the same in principle.
But you do not have essentially equations for the finite dimensional distributions to characterize the processes.
For the finite dimension.
Yeah, I mean many point distributions, like 2 points, 3 points, etc., like correlations, for instance, etc.
I think they can be worked out, but at the moment we have the generalized master equation for the P that I've shown, and then I think in the paper is also okay. I would have to check the one for the partial probability density waves in both directions, and that's it. Actually, that was in one dimension. Yes, and then higher dimensions that would be more complicated.
Okay.
Yeah. I would have to check, but that's an interesting question. But actually, this is also known for the Cattaneo equation, right? That this is a non-trivial problem. So
yes,
indeed, you're right. Yeah. I mean, this may be non-trivial. Yes.
Thank you very much. However, thank you.
Interesting question. Yes, thank you.
Thank you. And we have one more question from Adrian in this case.
Yeah, hi, Rainer. Thanks for the nice talk. So I had two questions. So one question, when you talk about the anomalous diffusion at the end, is this something you can show from the master equation, or is this just established numerically?
Good point. So I mean, we had 3 models, and it was really, really mixed. I have to check actually. So it really depended. Here, this was only a numerical results for the subdiffusive Levy walks. We don't have any theory yet. For this one, we do have both a theory and numerical results, and they match nicely. Well, I didn't show you the graphs because of lack of time, but they're in our paper. And here, I think we have only simulation results. So, but we believe that analytical results could be worked out for the second moment, but it has not been done yet.
So there are complications when you calculate the second moment, I mean.
Well, we haven't done, we thought about that, but then we kind of ran out of time and we didn't do it. So we do believe that it could be done, but it has not been done yet. Yeah.
And second question, so can you also include variations in the velocity? I mean, let's assume you draw the velocity from a distribution itself, which may be bounded if you want to avoid the velocities.
Yes, I mean, here we do that here, that we play around with the velocity. And here we do exactly that, that we choose the velocity from as a Markov chain dynamics. Yes, I mean, you can definitely plug this in. Yeah, that's a big advantage of this frame, I would think. Of course, you could also do that for standard Levy walks, and it has been done to quite some extent.
Okay, thanks.
Thank you very much.
Great, thank you. I don't see any other questions online. Anybody in the room? No. Okay, no questions. So let's thank all the speakers of today.
Thank you.
Thank you all. And now we will go for lunch. And there will be an open question session if you guys want to join later.